Before we solve this example, let's recall two key ideas about forcing terms in differential equations. The unit step function switches a forcing term on at a specific time, staying at 0 before that time and jumping to 1 after it. The Dirac delta models an instantaneous impulse, a sudden burst of force applied at a single instant in time. Now let's solve an example using both of these ideas together. We want to solve the derivative of y plus 2y equals an impulse at time 3, with the initial condition y of 0 equals 0. Taking the Laplace transform of both sides and using the fact that the transform of an impulse at time 3 is e to the power of negative 3s, we get an equation for capital Y of s. Solving that equation for capital Y of s gives capital Y of s equals e to the power of negative 3s over s plus 2. To invert this, first ignore the time shift and invert the unshifted part, 1 over s plus 2. The inverse Laplace transform of 1 over s plus 2 is e to the power of negative 2t. Now we reattach the time shift using the second shifting theorem. This gives the final solution, y of t equals e to the power of negative 2 times the quantity t minus 3 multiplied by the unit step function starting at time 3. Let's check this solution in two parts. First, before the impulse arrives, that is, for time less than 3, the unit step function is 0, so the solution is exactly 0, which matches our initial condition. Second, after the impulse arrives, for time greater than 3, the unit step function equals 1, and the solution becomes e to the power of negative 2 times the quantity t minus 3. Taking the derivative of this expression and adding 2 times y gives 0, confirming it satisfies the homogeneous equation for every time after the impulse.